Please.
Thank you very much. And thanks so much for running the whole show. So I speak about the huge results. So some new slides. So it's about the attacks on the L2 norm estimation in sketches, and it's a joint work with Sarah that is there and with. So first I'll give some background on why we're interested in this problem. Sketches map data to the small representation. In this talk, the data will be vectors for the two estimations. For property F, we want the sketch to be such that the property can be estimated sketch. And the design goals for sketches is that they are small, much smaller than the data, that the estimation is reasonably accurate, and also that there is some property of composability. Here we have linear sketches, but basically when you have data that shows up in different places, we want to be able to combine the sketches to get the sketch of the combined data, and the linear sketches give it to you kind of automatic. Many problems have random sketches. There are no deterministic sketches for them. They have these sub-problems. So what is the random sketch mean? The random sketch is a specific distribution over basically deterministic spreading. So you specify the distribution. So, and the property that the randomized sketches give you is that for any data, if you pick the sketch randomly from that distribution and you do your estimation, you're good with high probability. And usually we get that the delta, which is the error probability, is kind of exponentially small in the sketch type. So these are randomized sketches. And this guarantees hold when we don't know what the sketching matrix is when we pick the data, when we have the data. The data is kind of the sketching map is independent. So there are some properties that are very used in practice for sketching, for which there are no small deterministic sketches. For example, a cardinality estimation, L2 norm estimation, L2 regulators, we only, I mean, there are no small deterministic sketches. And what this means that once we pick, and another point is that we need to stay with the same often in many applications, especially in industry, we want to stay with the same sketching map to sketch multiple data sets. So we kind of fix the sketching map. And the point is that because that is exactly what facilitates composition. We cannot change the sketching map. And for any sketching maps, and this means that for any sketching maps, there are bad inputs exist. So if we can see the sketching maps, we can easily find bad inputs. Okay, so now here this workshop is all about the adaptive setting. So this is the model we use. It's not a pure streaming model. There are queries, which in our case are just vectors. And they are kind of processed in sketch space. For every vector, we get a sketch, and then we apply an estimator to the sketch. And this is the same model that Sarah and Miguel talked yesterday, but I'll kind of review it, especially with each participant kind of each component kind of knows. So we have a player, which is basically the attacker in our case, which basically specifies the query vectors. The player, the attacker, does not know crucially the sketching matrix. But it knows the input, and it knows the response, the estimate that it gets. There is some third player here, which is the system, which kind of does the sketching. It gets a vector and it computes the sketch. And then there is the query responder. The query responder knows the sketching map and its job, but it doesn't know the data. And it returns estimate of the property based only on the sketch. So about the animation. So the positive results for these settings. You've seen it this yesterday, right? So if we have k copies of the sketch, we can just use up each, if we maintain k copies of the sketch, like a meta sketch like that, we can always use one sketch for each query, and then we rotate the adaptive settings. And the advanced one is if you maintain k copies of the sketch, we can answer a quadratic number of adaptive queries. And this follows from subtractive result by blank here. And I missed your talk, sorry. And by results for statistical queries together with the very nice framework of the time and also here. That basically distributes in samples to any random sketches. So, okay, so we have a generic quadratic upper bound for everything, and when is it also a barrier? So in some cases it's not a barrier, like in Lori's talk yesterday, we saw how to we saw that if you construct another algorithm, adaptivity is not an issue. The fact is for some problems it is. So is this quadratic the right answer? And the way we expose vulnerabilities is by constructing the attack. So we know that the quadratic is typed for statistical queries via fingerprinting code results. The hard one, yeah, and okay, so these are like so now we talk about the attacks, the attack model. There are queries which are processed in sketch space. The attack size is the number of queries we need in order to compromise our sketching map. Compromising the sketching map means forcing incorrect response. So but you know, we can think about multiple attack types. First, the scope of the attack, which family of maps it applies to. So we can look at the B class, like all matrices, or we can look at the specific distributions like JL or LMS for L2 specifically. The attack can be tailored or it can be universal. What we mean by that? A tailored attack only applies to one very specific. The responses are a very specific estimator. They are for fixed estimator. Universal attacks allows the query responder to be adaptive and strategic and do anything it wants with the sketch, looking also at the attack sequence till now. Another property is that very simple attacks are single batch, meaning that all the attack queries are specified or sampled in advance, or they can be fully adaptive to the responses. Why I care about single batch? Because single batch attacks often can kind of be recreated just by watching normal workloads of the data. It's like, and adaptive attacks usually require actual active adversarial. So it's nice to know when we can use single batch attacks. And then another property is the product of the attack, which ideally we want something that forces a constant error rate, a large error rate on a distribution on which any estimator has a large error rate. or otherwise, or like a simpler goal is kind of just construct one adversarial input with respect to say standard or optimal. Okay, so this is kind of the taxonomy. And this is an overview of prior work. So Morris, Hart, and David here in 2013 showed that for L2 sketches attacks, they gave an attack that works for any sketching map, any matrix. The query responder is not restricted. The product is, it works against any estimator. It's fully adaptive attack. But it uses the only issue that is suboptimal with it is, I mean, except for the single but it is not attackable. It's that the number of queries is a large polynomial. It's not quadratic. And the question is there a quadratic size attack? That's what we want to solve that that has this problem. Yes, the Jelani student and Jelani had a specific attack on the JL matrices. This attack only uses the standard estimator of JL, like the responder just returns the exact responses of the JL, JL norms of the sketch, right? And the product of the attack is just by the input for that. This attack is a single batch and it uses a linear number of queries. Why? Because this exact attack that use the sketch in the best possible way to return the most accurate answer you have. What we can see is that usually the attacks they can be compromised. This is also the case for statistical queries, not it. Okay, Omri and the co-authors did a similar thing for the AMS attack. That attack was not single batch, if I recall correctly. It's also linear number of queries and we compromise. In some work with Uri and others, Angelani and Tomash, a couple of years ago, we did a quadratic size attack on the AMS sketch, where so the query responder is completely unrestricted, but then it can be strategic, but then it's a single batch attack. But then the product only compromises kind of the standard estimator for the AMS, which is kind of the optimal estimator. And it uses a quadratic number of queries. And then the question we ask here is this can be extended to any sketching map, not just AMS map. And basically in this work that I talk about here, we show that this can be extended to any sketching matrix. Any sketching matrix and the query responder is completely unrestricted. It can be strategic, it knows the distribution, the attacker uses it. It knows everything. And it's a single batch attack. But in the end result, it outputs a single vector, we call it adversarial vector, that compromises basically the optimal estimate. The optimal estimate for this distribution is way off. So okay. So for linear sketches, there are the parts here, the component, the sketching map is a matrix, the queries are vectors, the sketch is just the matrix multiplied by the vector. It has dimension k, the input has dimension n, much larger, and the property that we care about is the L2 norm. Okay, and this is the kind of the main results in more details. So we have a single batch attack. The attack kind of samples the distribution and then samples tilde or K-square IID queries from that distribution. And it has the property that it works for any sketching matrix. Any sketching matrix such that the data dimension is quadratic in K, and it works so with any strategic adaptive query responder. And then the result is the responder either has some this constant error rate. Of course, if the responder chooses to return 0 all the time or something, we can't do anything, right? So either the responder has a constant error rate, or the attacker constructs an adversarial input, and that's a restrictive part of the result. An adversarial input is one where the optimal estimator for that particular sketching matrix and the distribution is kind of way off. So this is what yes.
Can I ask a quick question?
Yeah.
Are you finding something specific about like something in the kernel, or are you just, you don't care?
Yeah, the attack doesn't care. That's a nice thing about it. It's yeah, basically it does reveal something, right, about A, but it's yeah. So I will show the attacks. Okay, so now components of the attacks, kind of the way we construct the queries. So we think about the queries, the vectors, as the signal and noise. If the sketching matrix is very long, we just look at the first n square columns in our query vector, the rest are 0. We sample the signal column, because we don't know the matrix, so we kind of have to sample. We sample the signal column out of this first square. And then the queries are produced as follows. They are sampled IID. We first sample a signal value from some distributions, think about constant range. And then we sample Gaussian noise for the rest of the first vector entries. Its magnitude is kind of smaller than the magnitude of the signal. And our query vector, so we sample the signal location, and then our query vector looks like that. The signal location of the W and the Gaussian noise. Okay. So this is the data distribution used. It's basically very similar to data distribution used in other attacks, including data distributions that are used for image classifiers. And this is also why I kind of want to understand this phenomenon better in some way. Basically, you just take the image, you add multiple noises, you look at how the prediction changes. Okay, so now we made a query responder task like we did with the cardinality sketches. Very, very easy. Basically, it's just that queries on the signal and correct responses. If the signal value is above some range, we want the responder to return 1, and if it's below, let's say it's above C2A, we want it to return 1, and if it's below some A, we want it to return -1, and otherwise, either way is a correct response. This is what is considered the correct response. So we make the responder task easier with kind of the result is responder. So now what is an estimator? An estimator basically maps sketches with our k-dimensional vectors to -1 and 1. Okay? So this is like a fixed estimate. So why we can just think about estimating the signal and it's almost like estimating the norm, because the norm of the noise is kind of basically very concentrated, it's kind of fixed. And it's smaller than the norms of the signal from the range that we pick. So basically it's like estimating norm is that we can just think about, we just need to estimate the signal, and it's almost the same level. Okay, so this is the attack. I think we say it's very simple. We sample the attacker samples vector, samples a signal coordinate, and then samples vector according to this distribution. The system for each time, the system computes the sketch. The responder is allowed to choose a different estimator map each time for each query based on the interaction so far, based on knowing the query distribution. It gets a sketch and it sends either -1, +1 back to the attacker. And basically what the attacker does is basically tracks a sum, a weighted sum of the noise vectors by 1 or not. So basically the memory the attacker uses is just the base one. Okay. So kind of a high level why this works. So once we fix the sketching matrix and the signal column, and we look at this type of query distribution, we can think about the sufficient statistics that we can get from the sketch on the signal. We can think about the sketch as kind of a parameterized distribution, parameterized by the signal value, and then you want to estimate the parameter which is the signal, and the sufficient statistic is just like a linear statistics of the sketch. Basically, it's a linear product of the sketch is vector, and that's all the information that is available in the sketch for the signal. And so the first component of kind of work, we need to have some variance here. So basically for most columns that we can choose, the variance of this optimal estimator must be, like, if it's constant, then it's, it's constant, it's signal value or norm values, then it must be sufficiently large. So most our choice of column vectors would be bad, because if you think about a linear sketch can just return us we can have like a row in the sketch that just like picks one column and then we return its exact value. But basically for almost all columns, we must have sufficiently high variance in the optimal estimator. Like the information present in the construct of sketch on only one on the value in a particular column has on average to be at least the most one. The second component we kind of need to make the claim work is what we call the gain lemma. Is that the once if the estimator is correct, means it responds correctly on all queries except maybe for a very small fraction. Then the kind of the bias of the noise vector is must be correlated with the response. Bias of the noise vector is kind of the estimator just applied to the noise, because this is basically just the noise of the optimal estimate, the error of the optimal estimate. So if the error is positive, we get the estimate is higher than we expect on average, and then we expect S to be +1, and if it's if the error is kind of negative, kind of tends to be lower than W, then S is more likely to be -1, and these are very tiny correlations. Yeah, if the responses use the full information in the sketch, we get very high correlation, but if without any restriction, with the restriction of only returning correct estimates with a noise sketch and then the response and then then the correlation is lower. Okay, and basically the punchline is that this adversarial vector that we construct, which is basically a signed sum of all the noise vectors that we have, according to the direction of the prediction. So if you look at that, the bias, the tiny biases that we know exist from the first component on every query kind of add up linearly. And the deviation, like standard errors, they increase like the square root. This is also therefore, if we do enough such vectors, in our case, it came out to quadratic, we get a higher. This type of argument is used in was kind of used also in fireworks. In this work, we made it. The new thing is that we made it kind of work from arbitrary matrices. Okay, so we applied this attack for on JL and robustified JL, robustified JL follows kind of the robustification framework of URI. It just adds noise to the final estimate to kind of hide the sketching matrix. So we can see that the attack kind of works. This is kind of the error. One is no error, you will be at 1. So as the attack progresses, as there are more queries, the error of the standard estimator goes faster, and the robustified estimator, the error goes lower. It depends how much noise we add to the final estimate. Okay, some open problems here. So to get, so I mean, basically this kind of work kind of did the most, I think, that we can hope for with a single batch attack. We have to have an adaptive attack to get a result like David did, that compromises any estimator. And the question is, of course, if there is such a quadratic attack, that's still open. So another thing that kind of disturbed here is that the noise support. We use the quadratic noise support, quadratic size noise support, k-square. Ideally, we want that to be k, because this is kind of the memory the attacker needs. And that now it's quadratic in the size of the sketch, but ideally you want it about the size of the sketch, put them all on kind of more equal footings. The result that we presented yesterday, for example, had case memory, the attack needed. And the only component in the proof where we actually needed the k-square was we use this general lemma because basically we want this property that the norm of the sum of the noise vectors kind of increases like square root. But we don't use the norm of the sum of the noise vectors. We have kind of a sign sum with plus and minuses that are correlated with things. And for that to work with arbitrarily placed plus ones and minus ones, we need kind of the vectors to be long enough. It's a kind of a general boundary, and that's and we need it to be quadratic. Obviously, if the noise vectors had only support 1, we could just put plus 1 where it's I mean, we could completely make, we could just match the sign with the sign of the value and then get the norm to increase kind of more. So if so this is where the quadratic came from, and maybe for the particular correlations of things we need here, maybe we could just move on. That's the hope. Another thing here, which kind of was also motivation for the whole work, is that this type of attack structure was used in multiple places, including for attacks on image classifiers, like you have a picture of a frog and you combine, you do this type of attacks, and then the classifier says it's guacamole or something, right? So I would like first to, and the explanations given in that literature and the CNN image classifications were completely very different. Some of them were very, very different than the explanations we have here for this vulnerability. And you know, the CNNs are of course not linear, but they are locally linear. So maybe this is kind of part of the explanation. And maybe there is some kind of more unified explanation for this. Basically, it's like fingerprinting style attacks, and we apply them, we change them a little bit, and we apply them in different places, but maybe we can have some unified view across problems, not just for norms, also for images. I don't know. And maybe with that understanding, we can find kind of good ways to improve robustness of maybe classifiers. I mean, by injecting noise either to the input or maybe injecting noise inside the architecture to kind of make it more robust. That's the thoughts. Okay.
Questions? So this may be like a more generic question, but like in your industrial experience, do you see like cases where people potentially might want to attack these types of sketches, or there is needs like within your company, I guess, or in general to defend against these types of attacks?
So so one of the building sketches, they use it over years and they use the same sketching map. And this is an issue. But we didn't see attacks, but like in principle, like sketches are used in networks, inside networks, sometimes inside network routers to maintain statistics. And if you kind of like implement, like if you can implement such attack by basically observing normal traffic, maybe you can inject traffic that can inject a little amount of traffic that would kind of distort things. So I mean, for L2, for cardinality sketches, for sure, it can be a big issue. For L2 attacks, for L2 attacks, basically like image network is I think the most practical example. I mean, it's not L2, but I mean, I don't know, maybe you go to an airport and there is an image and you can add some noise that will make you look like someone else. Yeah, not bad.
Other questions? Thank you. If you don't use, so you use Gaussian, if you don't use a Gaussian distribution attack, the discrete distribution,
I would suspect so, but yeah, I'll see it will be more painful. So maybe you can do it.
Okay, thank you.